In 1905, something surprisingly small revolutionized the world of sports and beyond. It was the discovery that simple dimples on golf balls could dramatically alter their performance, a breakthrough that made golf balls fly farther, faster, and with more control. But what if those same tiny indentations held the key to transforming more than just your weekend swing? This video is a deep dive into how engineers and scientists are trying to harness the power of dimples, not just for sports equipment, but for modern propulsion. From wind turbines to marine propellers to drone blades, researchers are exploring how manipulating surface airflow can reduce drag, boost efficiency, and even prevent damage in extreme environments. So buckle in. Today we're exploring how something as simple as a golf ball could shape the future of clean energy, aviation, and maritime transport. Let's start with where it all began. Over a century ago, optician William Taylor noticed something strange on the golf course. Older, scuffed-up balls flew better than the pristine, smooth ones. Curious, he built a DIY wind tunnel in his lab, using smoke trails to visualize how air moved around different surfaces. What he discovered would change the game. Those little dents, what we now call dimples, helped air cling to the ball longer, reducing the size of the low-pressure wake behind it and slashing drag dramatically. By the 1930s, virtually every golf ball had dimples. They became the gold standard, not just for stability, but for maximizing distance. So naturally, engineers started wondering, if this works so well on a ball, why not on other objects? To understand that, we need a quick refresher on how drag works. When an object moves through air like a ball or a propeller, it encounters two main types of drag: pressure drag and skin friction drag. Pressure drag happens when the air can't stay attached to the surface and peels away, forming a wake that pulls back on the object like a parachute. This is especially bad on blunt shapes, like a smooth golf ball. Skin friction drag, on the other hand, is like microscopic rubbing between the object's surface and the layer of air moving over it. Think of it like sliding your hand across a table. On long, narrow surfaces like airplane wings or propeller blades, skin friction becomes the dominant issue. Here's where dimples come in. They create a turbulent boundary layer, a thin, energized layer of swirling air that clings tighter to the surface. For a ball, this helps reduce pressure drag, because the air doesn't separate as early. That's why golf balls can fly nearly twice as far as their smooth counterparts. But here's the catch. For streamlined shapes like airfoils and propellers, the air is already more likely to stay attached, so pressure drag is less of a problem. In those cases, adding dimples could increase skin friction and potentially hurt performance. That's why, for years, engineers were hesitant to apply dimple tech to aviation or marine designs. But research is changing that. Let's look at some of the more promising areas, starting with propellers. In recent years, simulations have become powerful tools for testing new designs. A 2020 study used computational fluid dynamics to simulate how dimples affected drone propellers. At high angles of attack, where the blades are cutting into the air steeply, the researchers found that dimples improve the lift-to-drag ratio by nearly 40%. That's a huge gain in aerodynamic efficiency. Still, simulations aren't enough. The real-world performance of dimpled surfaces can depend heavily on things like airflow speed, shape, surface material, and even environmental conditions like humidity or temperature. So the question became, where can dimples really shine? Surprisingly, the biggest benefits may not come in the air, but underwater. Let's talk about cavitation. When ship propellers spin fast through water, they create areas of low pressure where water turns into vapor bubbles. These bubbles then collapse violently, causing noise, vibration, and even permanent damage to the blades. But here's the exciting part. A 2025 study showed that adding tiny dimples to the tips of marine propellers dramatically reduces cavitation. Up to 95% fewer bubbles formed during operation, all with minimal impact on overall performance. The idea is similar to golf balls. Dimples disturb the flow in a helpful way. They generate microvortices that keep the water attached to the surface longer and reduce sudden pressure drops that cause cavitation. And it doesn't stop there. Engineers are now combining inspiration from golf balls with ideas from nature, specifically dolphin skin. In China, researchers developed a flexible propeller coating embedded with microscopic structures just 0.1 to 0.2 millimeters wide. These structures guide the formation of turbulence in a controlled way, keeping the boundary layer thin and stable. The result? Less friction, less drag, and more efficient propulsion. They tested the coating on a 300,000-ton cargo ship over 200 days of real-world voyages across 35,000 nautical miles. The outcome? A 2% reduction in fuel use. That may sound small, but for massive ships that consume thousands of tons of fuel, it adds up fast. With a $20,000 application cost, the coating is projected to save up to $140,000 in fuel annually, and it's not just ships. Wind turbine blades have also started experimenting with similar surface roughness techniques. A German company called SmartBlade has fitted vortex generators, tiny fins that disturb airflow, to over 3,000 turbines worldwide. These features, placed strategically near the root of the blade, help energize the boundary layer and boost torque generation. In a global study of over 100 turbines, they saw average energy production gains of 2%. That might not sound dramatic, but on a wind farm it means millions of extra kilowatt hours per year. What's exciting about all this is that we're starting to understand how to manipulate the invisible forces around our machines. Whether it's through dimples, microfins, or biomimetic textures, engineers are finding clever ways to make air and water work for us, rather than against us. But like any emerging technology, there are still unknowns. We don't yet know how long these coatings last in real-world conditions. Salt, sand, algae, and temperature extremes could all affect durability. And for some applications, the extra skin friction from dimples might outweigh the benefits. Still, the trend is clear. Surface science, once the domain of niche sports equipment, is now powering innovation across transportation, energy, and aerospace. And it all started with something as humble as a battered old golf ball. If you're still watching, consider subscribing. It's free and helps support this kind of content. And if this video piqued your curiosity, check out the one on how SpaceX tech is revolutionizing home heat pumps. Thanks for watching and stay curious. And